this is Nathan, and I'm continuing the series on maximum likelihood estimation. For this video, I want to give a very simple example of what maximum likelihood estimator is trying to do. In this very simple example, we have two coins. One will return heads with probability 0.9. And the other situation is that the coin will return heads with probability 0.1. So the question we're trying to answer is, given that we've flipped the coin a number of times and we have some sample, which of these two weights, 0.9 or 0.1, is most likely? So let's say we flip the coin 10 times. And we get 7 heads. Intuitively, it's more likely that we have coin 1 because situation 1 is much more likely to produce an outcome that has 7 heads than coin 2. And if we do the math to find the probability under coin 1 that we would get 7 heads and compare it to the probability under situation 2 that we would get 7 heads, our intuition can be justified. We could write probability under coin 1 of x equals 7, where x is the number of heads, is equal to 10 choose 7 times 0.9 to the 7th times 0.1 cubed, while probability under coin 2 that x equals 7 is equal to 10 choose 7 times 0.9 cubed times 0.9 cubed times 0.1 to the 7th. It's because this is a binomial distribution with n equals 10, p equals 0.9, and this is binomial distribution with n equals 10, p equals 0.1. Now, if you compute these numbers, for coin 1, I get about 0.05740. For coin 2, I get 0.00001. So clearly, situation 1 is significantly more likely to occur. So generalizing this very simple example a little bit, what if instead of knowing that p is either 0.9 or 0.1, we have that p is some number in 0 to 1, because this is the possible values that the parameter p can hold. And the question is, what is the most likely outcome? What value of p would maximize, in our case, the PMF? PMF being 10 choose 7, because we flipped the coin 10 times and got 7 heads, p to the 7th, 1 minus p cubed. What value of the parameter, in our case p, will maximize the PMF or PDF of the sample that we've drawn, given the results from the experiment? So we are going from a sample with a known distribution. In this case, it's a binomial distribution, and unknown parameters. In this case, we don't know what p is. And trying to make an inference about what the parameter will look like. So infer about the parameter. So to do this, I'm going to introduce some notation that's called the likelihood function. So we write L of theta, where theta is parameter that we want to estimate, semicolon x, because x is data from the sample that we already know. And our goal is to maximize the likelihood function. So from Calc 1, the way to maximize a function is to, or find the maximum value of a function, to be more precise, is to take the derivative, set it equal to 0, right? So we can do that, and that will get us the right value of our parameter. But from the last video on logarithms, the max value of theta that maximizes this likelihood function is equivalent to the maximum value of theta that for the log likelihood function, the natural log of this likelihood function, because this likelihood function will always be greater than 0. And as it so happens, this log likelihood function, as we call it, also can be written as lowercase l of theta semicolon x, is oftentimes significantly easier to find the maximum of. So the question now is, what is this likelihood function? Well, as it so happens, this likelihood function is equal to the joint PMF or PDF. I'm writing PDF here, but it's the same if it's a PMF of the sample x1 through xn with theta, the unknown parameter, being the parameter. So then, L, lowercase l, of theta semicolon x is going to be the natural log of this PDF. Semicolon. So to find the maximum for this log likelihood function, we will take the derivative with respect to theta, set it equal to 0. So going back to the example that we started this video with, right? Starting to run out of space, but we have a binomial distribution with n equals 10, and p, we don't know p, but we know p is somewhere in between 0 and 1. And for the sample that we took, we got 7 heads. So the PMF is 10 choose 7 times p to the 7th times 1 minus p cubed. Right? And this PMF is our likelihood function. we will write L of P, because P is the unknown parameter in this case, semicolon X, where X is the sample that we took. So then, taking the log likelihood function, L of Px is equal to the natural log of the likelihood function, which is equal to natural log of 10 choose 7 p to the 7th 1 minus p cubed, which is equal to log of 10 choose 7 plus 7 log of p plus 3 log of 1 minus p right now. Because we're looking to find the maximum, we're gonna take the derivative. This 10 choose 7 term has no p's in it, so the derivative is 0. This 7 ln of p term, the derivative is 7 over p. This 3 times ln of 1 minus p, the derivative is negative 3 over 1 minus p. Set this equal to 0, so we get 7 over p is equal to 3 over 1 minus p. Multiply the denominators up, and we get 7 minus 7p is equal to 3p. Let's add these 7p's over. We get 7 equals 10p, or p hat is equal to 0.7. And this results that the most likely probability of getting heads on any coin flip being 0.7 makes a lot of sense in our case, because we flipped the coin 10 times and got 7 heads. So intuitively it makes sense that the most likely proportion, if we flipped the coin 1,000,000 times, would be that 70% of those flips would be heads.